Introduction to GCP Load Balancers. Welcome to our comprehensive guide on Google Cloud Platform Load Balancers. Think of load balancers as intelligent traffic orchestrators that distribute incoming requests across multiple backend instances. The slide shows 4 fundamental benefits. High availability ensures your application stays online even when individual servers fail by automatically routing around failures. Scalability handles traffic spikes by distributing load across multiple backend resources automatically. Global reach uses anycast IPs to route users to the nearest healthy backend automatically. This means a user in Tokyo gets routed to Asia, while a user in London reaches Europe, all using the same IP address. Security integration with Cloud Armor provides DDoS protection and web application firewall capabilities directly integrated with your load balancer. The diagram illustrates the basic concept. Internet users connect to the GCP load balancer, which intelligently distributes traffic across 3 different backend services, each containing their own instance groups. This provides both high availability and scalability. Google Cloud offers the most sophisticated load balancing portfolio in the industry, with solutions for every architectural pattern from simple regional deployments to complex global multi-tier applications. The Load Balancer Decision Tree. This is the most critical slide in the entire presentation. The decision tree that will guide every load balancer choice you make on the exam and in real life. The flowchart shows how every decision flows from 3 fundamental questions. Start with traffic source. If traffic comes from the internet, you need an external load balancer. If traffic comes from your VPC or internal network, you need an internal load balancer. For external traffic, ask global or regional. Global means you have backends in multiple regions and want automatic failover. Regional means everything is in one region. For global external, the protocol determines your choice. HTTP/HTTPS leads to global external HTTP/SLB. TCP with SSL leads to external SSL proxy LB. And TCP without SSL leads to external TCP proxy LB for regional external. Any layer 4 protocol. TCP, UDP, ESP, GRE, ICMP leads to regional external LB for internal traffic. Decide between layer 7, HTTP/S, or layer 4, TCP/UDP. Layer 7 leads to internal HTTP/SLB, which can be regional or cross-region. Layer 4 leads to internal TCP/UDP-LB. Master this tree. It will answer 80% of load balancer questions on the exam. Quick Decision Guide. Let me walk through this decision process step by step, as this mirrors how you should think during the exam. Step 1. Traffic source. Ask, is my traffic coming from the internet or from within my VPC? Internet traffic from users anywhere on the web needs external load balancers. VPC traffic from internal services, or on-premises, needs internal load balancers. Step 2. Geographic scope. For external traffic, ask, is my application global or regional? Global deployment means backends in multiple regions like US Central 1, Europe West 1, and Asia East 1, with automatic geographic routing. Regional means all resources in one region like just US West 1. Step 3. Protocol type. This determines features versus performance trade-offs. HTTP or HTTPS protocols enable layer 7 features like URL routing, header manipulation, and SSL termination. TCP or UDP protocols can use either proxy features or pass-through performance architectures. The quick answers summarize the most common patterns. Global and HTTP or HTTPS means a global external HTTPS load balancer. Regional and UDP means a regional external load balancer. Internal and HTTP means an internal HTTP or HTTPS load balancer, and internal and TCP means an internal TCP or UDP load balancer. Memorize these patterns. They cover the majority of real-world scenarios and exam questions you'll encounter. Architecture overview. Understanding these three fundamental architectures is crucial for making informed load balancer choices. Global architecture leverages Anycast IPs. The same IP address is advertised from multiple Google regions simultaneously. When users make requests, Internet routing automatically delivers them to the nearest region. Users in Tokyo reach Asia. Users in London reach Europe, all transparently. Regional architecture serves traffic within a single region but distributes across multiple zones for high availability. You get a regional IP that serves traffic optimally within that geographic area. Internal architecture handles VPC to VPC communication. Your microservices talking to each other, applications connecting to databases, or internal tool access all use internal load balancers. The key insight is that each architecture pattern serves different use cases. Global for worldwide applications, regional for geographic-specific deployments, and internal for service-to-service communication. Understanding when to use which architecture is essential for both real-world deployments and exam success. The choice affects performance, cost, and available features. Proxy versus pass-through architecture. This fundamental concept differentiates load balancer types and determines their capabilities and performance characteristics. Proxy-based, or Layer 7, architecture terminates the client connection and establishes a new connection to the backend. Think of it like a sophisticated translator that understands your requests. It can modify them, add headers, handle SSL certificates, and make intelligent routing decisions based on content. The benefits include rich Layer 7 features like URL-based routing, SSL offloading to remove encryption burden from backends, advanced routing based on headers or content, and header manipulation for application optimization. Pass-through, or Layer 4, architecture forwards packets directly to backends without terminating connections. It's like an intelligent network switch that preserves the original connection while distributing traffic efficiently. Pass-through benefits include lower latency due to no proxy overhead, preservation of client IP addresses for logging and security, and support for any protocol including custom ones. The sequence diagram shows the difference. Proxy-based involves SSL termination and Layer 7 processing with new connections, while pass-through simply forwards packets, maintaining the same connection. Choose proxy for rich features. Choose pass-through for maximum performance. This trade-off appears frequently in exam scenarios. The Global External HTTPS Load Balancer is Google's flagship offering, designed for modern web applications that need global reach and sophisticated features. The architecture diagram shows the complete flow. Users from Asia, Europe, and the Americas all hit the same Anycast IP. Traffic flows through Cloud CDN for global content caching, then CloudArmor for security protection, then URL maps for intelligent routing rules. Finally, traffic reaches backend services that can span multiple regions: US Central 1, Europe West 1, and Asia East 1, each containing their own instance groups for high availability. Key features include Anycast IP providing global availability and automatic geographic routing, SSL TLS termination and offloading to reduce backend processing, URL-based routing and path matching for sophisticated traffic distribution, and WebSocket plus HTTP2 support for modern applications. The powerful integrations make this special. Cloud CDN for global content caching reduces latency worldwide. CloudArmor provides WAF and DDoS protection. Identity-aware proxy enables zero-trust access control, and traffic splitting enables a/B testing and canary deployments. This is your go-to choice for any global web application, API gateway, single-page application, or customer-facing service that needs worldwide reach with sophisticated features. Creating Global External HTTPS Load Balancer, Part 1. Let me walk through these G-Cloud commands step by step, explaining exactly what each parameter does and why it's needed. The G-Cloud Compute Instance Templates Create Web Server Template command creates a template for web server virtual machines. The machine type equals E2 medium specifies balanced compute resources. Network interface equals network tier equals premium. Subnet equals default ensures global network reach. And tags equals HTTP server. HTTPS server enable firewall targeting. The metadata startup script is crucial. apt-get update and apt-get install y nginx installs the web server. systemctl start nginx runs it. And the echo commands create both a main page showing the hostname and a health check endpoint. Creating managed instance groups with G-Cloud Compute Instance Groups managed create in multiple regions gives global footprint. The base instance name equals web server as provides consistent naming. Template equals web server template references are template. And size equals 2 sets initial capacity. Autoscaling with G-Cloud Compute Instance Groups managed set autoscaling handles traffic spikes automatically. The max num replicas equals 10 minutes num replicas equals 2 sets capacity bounds, and target CPU utilization equals 0.8 triggers scaling at 80% CPU usage. These commands build the foundation, the actual compute resources that will serve your traffic once the load balancer is configured. Creating Global External HTTPS Load Balancer, Part 2. Now let's complete the load balancer setup with the networking and routing components. The health check defines how the load balancer determines instance health. The port 80 request path /health means it makes GET requests to /health on port 80. The timing parameters check interval 30 seconds healthy threshold 2 unhealthy threshold 3 control how aggressively it monitors health. The backend service is the core component. The protocol HTTP port name HTTP defines the backend protocol. HealthCheck's web health check attaches health monitoring. Global makes it available worldwide. And enable CDN turns on global content caching. Adding backends connects instance groups to the service. The balancing mode utilization max utilization 0.8 distributes traffic based on CPU usage and limits instances to 80% utilization for headroom. The URL map defines traffic routing rules. This basic version routes all traffic to one backend service, but you can add path-based routing later. These components work together to create the intelligent traffic distribution system that makes global load balancing possible. Creating a global external HTTPS load balancer. Finally, let's complete the HTTPS load balancer by adding SSL certificates, proxies, and creating the final load balancer resource. First, we create the SSL certificate resource. Using the G-Cloud command, we request a Google managed certificate. Google automatically handles Let's Encrypt integration, domain validation, and renewal. The global flag makes it available for global load balancers. Next, we create the target HTTPS proxy. This resource connects your URL map to your SSL certificate. This component handles SSL termination. It decrypts HTTPS traffic, processes it according to URL map rules, then sends HTTP traffic to backends. The forwarding rule, created next, is the actual load balancer. We configure this rule with specific parameters. It assigns a specific global IP address, makes the load balancer globally accessible, connects to the target HTTPS proxy, and handles HTTPS traffic on port 443. An HTTP to HTTPS redirect improves security. Using another G-Cloud command, we create a URL map specifically for redirection. This automatically redirects HTTP traffic to HTTP pages as separate target HTTP proxy and forwarding rule resources handle the initial HTTP traffic on port 80. Together, these steps create a complete, production-ready global HTTPS load balancer with automatic SSL certificate management and HTTP to HTTPS redirection. External SSL Proxy Load Balancer. The external SSL Proxy Load Balancer handles global TCP traffic that requires SSL termination but is not HTTP-based. The architecture diagram shows the clean flow. Global clients connect to the Anycast IP. SSL termination happens at Google's edge. Then unencrypted TCP traffic flows to backends across multiple regions including ES Central 1, Europe West 1, and Asia East 1. Let me explain the G-Cloud commands shown on this slide. The health check command. G-Cloud Compute health checks create TCP SSL health check port 443. Uses TCP health checks since we are not dealing with HTTP. The regional parameter and timing control how aggressively the system monitors backend health. The backend service command. G-Cloud Compute backend services create SSL backend service protocol SSL, indicates this handles SSL termination. The parameters health checks SSL health check, global, and port name SSL complete the backend configuration. The SSL certificate can be self-managed using the command. G-Cloud Compute SSL certificates create SSL proxy cert certificate path to cert.pem private key path to private key.pem global. This is where you provide your own certificate files. The target SSL proxy command. G-Cloud Compute target SSL proxies create SSL proxy. Connects the backend service to the SSL certificates, handling the SSL termination process. Finally, the command. G-Cloud Compute forwarding rules create SSL proxy LB global target SSL proxy ports 443. Creates the actual load balancer on port 443. Use this setup for global TCP-based services that need SSL encryption but do not use HTTP. Examples include secure SMTP, IMAP, or custom encrypted protocols. Regional External Load Balancer. The regional external load balancer is fundamentally different from the global load balancers we've covered. This is all about high performance, pass-through architecture for regional deployments. Look at this diagram. It shows the clean, simple architecture. Regional clients hit a regional IP address, which forwards traffic through a regional backend service to instance groups across multiple zones within the region. The key insight is pass-through architecture. Unlike proxy-based load balancers that terminate and re-establish connections, this load balancer forwards packets directly to backends. Think of it as an intelligent network switch rather than a proxy server. Why does this matter? For gaming applications, every millisecond counts. Players notice latency above 50 milliseconds, and competitive gamers demand sub-20 milliseconds response times. Pass-through architecture eliminates proxy overhead entirely. This also preserves client IP addresses, which is crucial for anti-cheat systems, player geolocation, and security logging. Many games use client IP for region locking and cheat detection. Protocol support is comprehensive. TCP, UDP, ESP, for VPNs, GRE, for tunneling, and even ICMP. This makes it perfect for gaming, UDP, VoIP, UDP, custom protocols, or any high-performance application where latency trumps Layer 7 features. Let's create a regional external load balancer. I'll walk through the G-Cloud commands for this gaming server load balancer. Each command serves a specific purpose in building the complete solution. First, G-Cloud Compute addresses create game static IP region equals US Central 1 creates a regional static IP. Unlike global IPs, this is tied to a specific region, but provides consistent addressing for your players. The instance template creates game server virtual machines. The key parameters are: machine type equals C2 standard 4 uses compute optimized instances perfect for gaming workloads. Network tier equals premium ensures the best network performance. And tags equals game server enables firewall targeting. The managed instance group creates multiple game server instances with size equals 3 for initial capacity. Zone equals US Central 1 places them in a specific zone, though you typically create groups in multiple zones for high availability. The health check is critical. G-Cloud Compute Health Checks create TCP Game Health Check port equals 7777 checks if game servers are responsive. Region equals US Central 1 makes this a regional health check, and the timing parameters control how aggressively we check server health. The backend service ties everything together with protocol equals UDP for game traffic and load balancing scheme equals external for internet-facing traffic. Finally, the forwarding rule creates the actual load balancer with IP protocol equals UDP ports equals 7777, meaning any UDP traffic to port 7777 gets distributed to healthy game servers. Regional Internal HTTPS Load Balancer. Now, we're switching to internal load balancers, which handle traffic within your VPC. The Regional Internal HTTPS Load Balancer is the modern choice for microservices architectures. This diagram shows the sophisticated architecture. It's based on Envoy Proxy, giving you incredibly rich Layer 7 features for internal traffic. Internal clients connect to the Envoy Proxy, which processes requests and routes them based on URL maps to different backend services. The magic is in the advanced routing. You can route /API/payments to your payment service, /API/users to your user service, and /API/orders to your order service, all through a single load balancer endpoint. This makes the load balancer your internal API gateway. Beyond path-based routing, you can route based on HTTP headers, for instance sending version beta traffic to beta services, based on query parameters, or even perform traffic splitting for canary deployments. For example, sending 95% of traffic to the stable version and 5% to the new version. Security is enhanced with private internal IP addresses, so no internet exposure, SSL/TLS termination for internal traffic encryption, integration with identity-aware proxy for zero-trust access, and full VPC firewall integration. This is perfect for microservices because each service registers different paths. The load balancer handles service discovery and health checking, and you get sophisticated routing without each service needing to know about others. Okay, let's talk about creating a regional internal HTTPS load balancer. Let me explain each step in creating a regional internal HTTPS load balancer for microservices. First, the custom VPC setup. Created with the command "G-Cloud Compute Networks create internal VPC subnet mode custom" gives you better control than the default network. The subnet range 10.0.1.0/24 provides private IP space for your internal services. The instance template specifies no address, meaning instances get only private IPs, with no external IPs. This is a security best practice for internal services. The parameter subnet internal subnet places instances in your custom subnet. The health check is configured with port 80, request path/health, and region US Central 1. It is regional because this is a regional load balancer. Your microservices should expose a /health endpoint that returns 200 OK when healthy. The backend service has the critical parameter load balancing scheme internal_managed. This indicates the modern Envoy-based internal load balancer, not the legacy internal load balancer. The URL map creates routing rules. Start with default service for basic routing, then add path-based rules later with the G-Cloud command "compute URL maps" add path matcher for advanced routing. The target HTTP proxy connects your URL map to the forwarding rule, enabling the sophisticated HTTP processing. The forwarding rule creates the load balancer with load balancing scheme internal_managed, network, and subnet parameters to specify VPC placement, and address 10.0.1.100 for a predictable internal IP that your services can connect to. Cross-region internal HTTPS load balancer. The cross-region internal HTTPS load balancer enables internal services to span multiple regions, which is powerful for global internal architectures. This diagram shows how one load balancer configuration can route internal traffic to backends in multiple regions. Clients in any region can reach services in any other region through this unified load balancer endpoint. Perfect use cases include global data processing pipelines where services in different regions need to communicate, disaster recovery with automatic failover between regions for internal services, or global microservices where services are distributed but need to communicate. The key difference in the commands is using global resources. The G-Cloud Command Compute Backend Services create cross-region backend service. Global load balancing scheme equals internal managed creates a global backend service instead of regional. You add backends from multiple regions to this single global backend service with instance group zone equals US Central 1-A global and instance group zone equals Europe West 1-B global. The URL map and target proxy are also global, indicated by the global flag, creating a unified routing configuration. Then you create regional forwarding rules in each region where you have clients. Each forwarding rule points to the same global target proxy but serves clients in that specific region, providing optimal routing while using shared global configuration. Regional Internal TCP/UDP Load Balancer. The Regional Internal TCP/UDP Load Balancer provides the highest performance for internal traffic using pure Layer 4 pass-through architecture. This diagram shows a classic use case: database load balancing. You have multiple database replicas, primary and read replicas, and applications need a single connection point that distributes queries across healthy database instances. Why pass-through for databases? Database connections are long-lived and performance-sensitive. Applications maintain connection pools, and any proxy overhead impacts query performance. With pass-through, packets flow directly to database servers with minimal latency. This preserves client connections end-to-end, which is important for database session management, connection pooling, and transaction handling. It also supports any TCP-based protocol, PostgreSQL, MySQL, Redis, MongoDB, or custom TCP services. The load balancing is connection-based rather than request-based. New connections are distributed across backends, but existing connections stay pinned to their original backend, which is exactly what database applications expect. Perfect for database load balancing, message queues like Redis or RabbitMQ, caching layers, high-performance internal APIs, or any internal TCP/UDP service where performance is more important than Layer 7 feature. Creating an internal TCP/UDP load balancer. Let me walk through creating an internal TCP/UDP load balancer for database load balancing, which is extremely common in production. The instance template machine type N1 standard 2 is sized for database workloads, and no address ensures database servers have only private IPs for security. The startup script installs PostgreSQL, though in production you would use more sophisticated database setup. The managed instance group creates multiple database replica instances with a size of 3. In a real deployment, you would configure primary/replica relationships, but this example shows the load balancer perspective. The HealthCheck G-Cloud Compute HealthChecks create TCP/DB. HealthCheck uses TCP HealthChecks on the PostgreSQL port. The timing is less aggressive than web services because database startup takes longer and you do not want false positives. The backend service uses protocol TCP for database connections and critically load balancing scheme internal, not internal managed. This indicates pass-through architecture, not the Envoy-based proxy. The forwarding rule creates the load balancer with load balancing scheme internal, address 10.128.0.100 for a predictable internal IP, ports 5432 for PostgreSQL, and IP protocol TCP applications connect to 10.128.0.100 port 5432 and get distributed across healthy database replicas. The load balancer handles health checking and automatically removes failed replicas from rotation. This provides high availability for your database tier while maintaining the performance characteristics that database applications require. Shield Cloud Armor integration. CloudArmor is Google's web application firewall and DDoS protection service. Think of it as an intelligent security guard that sits in front of your load balancers. The architecture shows how CloudArmor analyzes all traffic before it reaches your load balancer. Attackers and legitimate users both hit CloudArmor first, which uses machine learning and rules to block malicious traffic and allow good traffic through. Let me explain these powerful G-Cloud commands. G-Cloud Compute Security Policies create Web Security Policy creates the container for all security rules. The rate limiting rule is fantastic for DDoS protection. Rate limit threshold count 100 rate limit threshold interval sec 60 means if any IP makes more than 100 requests in 60 seconds, and ban duration sec 600 bans that IP for 10 minutes. Enforce on key IP tracks rates per client IP. The geo-blocking rule expression origin.region code equals CN action deny 403 blocks all traffic from China. You can block or allow any country using ISO country codes. The SQL injection rule expression evaluate pre-configured EXPR SQLi stable uses Google's machine learning models to detect SQL injection patterns in requests and blocks them automatically. Attaching the policy with G-Cloud Compute Backend Services Update Web Backend Service Security Policy Web Security Policy enables protection for your load balancer. Cloud CDN integration. Cloud CDN is Google's global content delivery network that caches content at edge locations worldwide, dramatically improving performance for static content. The first command using G-Cloud Compute Backend Services Update Web Backend Service enables CDN cache mode equals cache all static enables CDN and automatically caches images, CSS, JavaScript, and other static files. The TTL settings control caching duration. Default TTL equals 3600, 1 hour default. Max TTL equals 86400, 24 hours maximum. And client TTL equals 3600, what browsers cache. Custom cache keys control what makes content unique. Cache key include host means example.com and www.example.com cache separately. Cache key query string whitelist equals version comma lang means only version and lang parameters affect caching. Other parameters are ignored for cache decisions. Custom response headers help with debugging. Custom response header equals x-cache-status CDN cache status tells you if content was served from cache, hit, or origin, miss, and x-cache-id provides unique identifiers for troubleshooting. Negative caching policy equals 404 equals 300, 410 equals 300 caches 404 and 410 errors for 5 minutes, preventing repeated requests for non-existent resources and reducing load on backends. This combination dramatically reduces load on backend servers and improves user experience, especially for global applications. Practical exam scenarios. These scenarios represent the types of questions you'll encounter on the GCP network specialty exam. Let me walk through the decision process for each. First, the global e-commerce platform requires a global external HTTPS load balancer. This is because a global user base needs Anycast IP for optimal routing, CDN integration for product images, CloudArmor for DDoS protection, SSL termination for HTTPS, and backends in multiple regions for high availability. Next, the real-time gaming server demands a regional external load balancer. This is because games need the lowest possible latency using a pass-through architecture, UDP protocol for real-time data, client IP preservation for anti-cheat systems, and regional deployment to minimize latency to the player base. For internal microservices, the requirement is a regional internal HTTPS load balancer. This is because traffic is VPC internal. REST APIs use HTTP or HTTPS. Path-based routing is needed for different endpoints, and SSL termination is required for internal security. Finally, Database load balancing requires a regional internal TCP/UDP load balancer. This is because database connections are performance sensitive, typically using a pass-through approach with the TCP protocol. You also need to preserve client connections for session management, and the traffic is internal VPC traffic. So, the overall exam strategy is to work through a decision tree systematically. First, determine the traffic source. Is it from the internet, which is external, or is it VPC internal? Then consider the scope. Multiple regions means global, while a single region means regional. Next, look at the protocol needs. HTTP or HTTPS indicates layer 7, while TCP or UDP indicates layer 4. And finally, evaluate the performance versus features trade-offs. Identity-Aware Proxy (IAP) integration. Identity-Aware Proxy provides zero-trust access control for your applications behind load balancers. Instead of relying on network perimeters, IAP verifies user identity and context for every request. The first command, G-Cloud Compute Backend Services Update Web Backend Service. IAP equals enabled. Global enables IAP on your backend service. This means every request will be intercepted and validated before reaching your application. The G-Cloud IAP Webset IAM policy command is crucial. It defines who can access your application. The policy file specifies that users with the role/iap.https resource accessor role can access the backend service. You can grant this to specific users, groups, or service accounts. IAP works by issuing signed headers to authenticated requests. Your application receives headers like x-goog-iap-jwt-assertion containing verified user identity. This enables your app to make authorization decisions based on authenticated user context. The OAuth setup, done in console, creates the identity provider integration. IAP supports Google accounts, SAML, OIDC, and corporate identity providers for seamless enterprise integration. This is perfect for internal tools, admin dashboards, or any application requiring authentication without implementing your own auth system. Monitoring and alerting setup. Effective monitoring is essential for production load balancers. These commands establish comprehensive observability for your load balancing infrastructure. The G-Cloud Alpha monitoring policies creates alerting policies from YAML configuration. The example policy monitors backend service error rates targeting your load balancer backends. The threshold configuration triggers when the error rate exceeds 5%. The duration means the condition must persist for 5 minutes before alerting, which prevents noise from transient spikes. The aggregation settings are crucial. Alignment period samples data every minute, per series aligner converts counts to rates, and cross-series reducer averages across instances. VPC flow logs captures 10% of network flows for traffic analysis. The logging aggregation interval batches logs for efficient processing. Uptime checks using the G-Cloud monitoring uptime command proactively monitor your load balancer endpoints from multiple global locations, providing early detection of outages. Custom dashboards visualize key metrics like request latency, error rates, backend health, and traffic patterns for operational awareness. Troubleshooting load balancer issues. When load balancers misbehave, systematic troubleshooting using these G-Cloud commands quickly identifies root causes. Start with G-Cloud Compute Forwarding Rules described to verify the load balancer configuration. This shows the forwarding rule, which is the load balancer, target proxy, and IP address assignment. The critical command G-Cloud Compute Backend Services Get Health reveals the health status of every backend instance. Unhealthy backends won't receive traffic, so this immediately identifies capacity issues. URL map validation with G-Cloud Compute URL maps validate source checks routing configuration before deployment. Syntax errors in URL maps cause traffic routing failures. SSL certificate issues are common. G-Cloud Compute SSL certificates describe shows certificate status, domain validation, and expiration dates. Look for status fields indicating provisioning or validation failures. Firewall troubleshooting with G-Cloud Compute Firewall Rules List filter helps identify connectivity issues. Load balancers require specific firewall rules for health checks 130.211.0.0/22, 35.191.0.0/16, and traffic flow. Log analysis with G-Cloud Logging Red provides request-level insights. Filter by resource type GCE backend service to see load balancer request logs including response codes, latency, and backend selections. The connectivity test with G-Cloud Compute SSH and curl validates end-to-end connectivity from client perspective, bypassing potential DNS or routing issues. Let's dive deep into understanding load balancing algorithms, which is crucial for optimizing performance and achieving desired traffic distribution patterns. Round robin distributes requests sequentially across backends. For example, request 1 goes to backend A, request 2 goes to backend B, request 3 goes to backend C, and then back to A. It's simple and effective when backends have similar capacity and request processing times. Least connections routes new requests to backends with the fewest active connections. This is superior for long-lived connections or when request processing times vary significantly. WebSocket connections, database connections, and streaming applications benefit from this algorithm. IP hash uses consistent hashing of client IP addresses to determine backend selection. The same client IP always reaches the same backend, unless that backend fails, providing session affinity without sticky sessions or session storage. Weighted round robin extends basic round robin by considering backend capacity. A backend with weight 2 receives twice as many requests as a backend with weight 1. You configure weights using the capacity scaler parameter in backend service configurations. When configuring backend services, the balancing mode parameter controls how traffic is distributed. For example, in a G-Cloud environment, you might set the balancing mode to utilization with a max utilization of 0.8. Utilization mode sends traffic based on CPU utilization, while RATE mode uses requests per second. Connection draining. Configured with the connection draining timeout sec parameter set to 300, gracefully removes backends from rotation, allowing existing connections to complete before instance shutdown. Anycast IP and global routing. Anycast IPs are the foundation of Google's global load balancing magic, enabling automatic geographical routing without client configuration. The diagram illustrates how the same IP address 203.0.113.1 is simultaneously advertised from multiple Google regions worldwide. When a user in Tokyo makes a request, Internet routing protocols automatically deliver traffic to the Asian region. A user in London reaches the European region, and New York traffic goes to Americas. This happens at the Internet routing level using BGP, which stands for Border Gateway Protocol. Google advertises the same IP prefix from multiple points of presence globally. Internet routers choose the closest path based on routing metrics, automatically optimizing for latency. The G-Cloud Compute addresses create global command creates these Anycast IPs. Unlike regional IPs tied to specific locations, global IPs provide automatic geographic load balancing and instant failover. When an entire region fails, BGP automatically withdraws the route from that region, causing all traffic to be rerouted to healthy regions within seconds. Users experience this as automatic failover without any client-side changes. Global load balancers leverage this for automatic disaster recovery. If your entire US Central 1 deployment fails, traffic automatically shifts to Europe West 1 and Asia East 1 backends without intervention. The user experience is seamless. They always connect to the same IP address but get routed to the optimal healthy location based on network topology and health. Advanced health checking strategies. Sophisticated health checking goes beyond basic TCP port checks to ensure backends are truly ready to serve traffic effectively. The HTTP health check with request path equals health host equals health.example.com enables application level health verification. Your application can check database connectivity, external service dependencies, and internal state before returning 200 OK. Custom host headers with host equals health.example.com allow virtual host routing to dedicated health check endpoints, separate from production traffic paths. This prevents health checks from interfering with application metrics. Proxy header configuration proxy header equals proxy_v1 provides backend servers with original client information in health checks, enabling more sophisticated health logic based on request context. gRPC health checks with G Cloud Compute health checks create gRPC service name equals my service v1 health check integrate with gRPC's native health checking protocol, enabling service-aware health validation. The timing parameters balance responsiveness versus stability. Check interval equals 10s determines check frequency. Timeout equals 5s sets maximum wait time. Healthy threshold equals 2 requires consecutive successes before marking healthy. And unhealthy threshold equals 3 needs multiple failures before marking unhealthy. Regional versus global health checks affect check frequency and source IPs. Regional health checks come from specific regions, while global health checks originate from multiple worldwide locations. Health check failure handling removes backends from rotation immediately, but continues checking for recovery. When backends become healthy again, they're automatically re-added to the rotation. Performance optimization strategies. Load balancer performance optimization requires careful consideration of architecture choices, configuration parameters, and integration patterns. Connection pooling with connection pooling enabled reduces connection establishment overhead by reusing connections between load balancer and backends. This is especially important for high-traffic applications with short-lived requests. The timeout configuration with timeout 30 seconds connection draining timeout sec 300 balances responsiveness with graceful handling. Short timeouts prevent slow backends from affecting user experience, while appropriate draining timeouts allow graceful shutdowns. Backend capacity optimization using max utilization 0.8 capacity scalar 1.0 ensures backends don't become overloaded. The 80% utilization threshold provides headroom for traffic spikes while maximizing resource usage. Session affinity with session affinity client IP or session affinity generated cookie ensures users consistently reach the same backend for stateful applications, reducing session synchronization overhead. HTTP2 enablement with HTTP2 enabled improves performance for modern web applications through connection multiplexing, header compression, and server push capabilities. Custom request and response headers optimize application behavior. Custom request header X forwarded proto-HTTPS informs backends about original protocol, while custom response header X cache status CDN cache status provides caching insights. Locality preferences with backend selection algorithms minimize latency by preferring geographically closer backends when multiple healthy options exist. Cost optimization and resource management. Effective cost management for load balancers involves strategic architectural decisions and efficient resource utilization patterns. Right-sizing load balancer types prevents over-provisioning. Use regional load balancers for single region deployments rather than paying for global capabilities you don't need. Regional external load balancers cost less than global alternatives when geographical distribution isn't required. The sustained use discount analysis shows that consistent usage patterns can reduce costs significantly. The preemptible flag for backend instances provides substantial savings for fault-tolerant workloads, though requires careful health check tuning. Autoscaling configuration with target CPU utilization equals 0.7, minimum number of replicas equals 2, and maximum number of replicas equals 10 balances cost with performance. Higher CPU targets reduce instance count but may impact latency during spikes. Network tier selection affects costs. Network tier equals standard provides regional egress pricing, while network tier equals premium uses global anycast routing with higher costs but better performance. Load balancer pricing varies by type. Global external load balancers charge for forwarding rules and processed data, while regional load balancers have simpler pricing models. Internal load balancers typically cost less than external alternatives. Traffic optimization through CDN integration reduces backend processing costs and improves user experience. Static content served from cache doesn't consume backend resources or trigger autoscaling. Resource consolidation using URL maps to route multiple services through single load balancers reduces forwarding rule costs compared to separate load balancers per service. Exam preparation best practices. Success on the GCP Network Specialty exam requires mastering both theoretical concepts and practical command execution scenarios. The decision tree methodology is your primary tool. Start with traffic source, internet versus VPC. Then determine scope, global versus regional, followed by protocol requirements, HTTPS versus TCP/UDP, and finally consider feature versus performance trade-offs. Command pattern recognition helps identify load balancer types. The parameter "global" indicates global load balancers. "Load balancing scheme" set to "external" means internet-facing. "Load balancing scheme" set to "internal managed" specifies modern internal HTTPS load balancers. And "load balancing scheme" set to "internal" indicates pass-through internal load balancers. Integration scenarios frequently appear on exams. CloudArmor requires global external load balancers. CDN integration works with HTTPS backends. IAP integrates with backend services. And VPC firewall rules must allow health check traffic from specific IP ranges. Common troubleshooting scenarios test your understanding of health check failures, SSL certificate provisioning issues, firewall rule misconfigurations, and backend service health status interpretation. Performance versus feature trade-offs appear in scenario questions. Gaming applications need pass-through for latency. Web applications benefit from proxy features. Internal microservices require HTTPS routing, and databases need TCP/UDP pass-through. The exam emphasizes real-world architectural decisions rather than memorizing syntax. Focus on understanding when to use each load balancer type and why specific configurations are appropriate for given requirements. Master comparison table. This comprehensive comparison table is your ultimate reference for distinguishing between GCP load balancer types during the exam and real-world implementations. The scope column differentiates global, anycast IPs, multi-region backends, from regional, single region, specific zones, and multi-region, cross-region internal only. This immediately narrows your choices based on geographical requirements. Traffic type distinguishes external, internet-facing, public IPs, from internal, VPC-only, private IPs. This is the first decision point in the decision tree and eliminates half the options immediately. Protocol support shows HTTP/HTTPS for web applications, TCP with SSL for encrypted non-HTTP traffic, TCP without SSL for custom protocols, and TCP/UDP for maximum protocol flexibility with pass-through architecture. Architecture differences are crucial. Proxy, L7, provides rich features like SSL termination, header manipulation, and advanced routing, while pass-through, L4, offers maximum performance with minimal latency and client IP preservation. SSL handling varies. Terminate and offload processes SSL at the load balancer for backend simplicity, while pass-through maintains end-to-end encryption or no encryption for performance-critical applications. Use cases guide selection. Global web apps need global external HTTP pages. Gaming requires regional external pass-through. Microservices use internal HTTP/HTTP pages and databases need internal TCP/UDP integration capabilities. Determine advanced features. CDN, Armor, and IAP require specific load balancer types, while pass-through load balancers offer minimal integrations for maximum performance. Memorize this table structure to quickly eliminate incorrect options and identify the optimal load balancer for any given scenario.